In this video, we'll talk about the case where the damping parameter vita is greater than omega naught, and we call this case overdamping. Now, if vita is greater than omega naught, then I know that vita squared minus omega squared is a positive number, which means the square root of this difference will give me a real number. And this is in contrast with what I got when I had underdamping. Now, this is familiar. This is the general solution to the differential equation that I found before. But now I want to look again at those two terms and see what sense I can make of it. I want to understand what this condition will tell me about the two terms. Now I can write this in a slightly different way. I can say C1 E. I can take the minus out, and I will show you why. T plus C2E. Again, I'm gonna take the minus sign out, so this becomes a plus. Now, this is what I have. Other than the two constants, I have E to the minus a number T and E to the minus a slightly different number T. So the important thing is that both of these have the following form: E to the minus something times T. Now, about this exponential, I know that the greater this is, the smaller the whole thing gets. And when I say greater, I mean more positive. Okay. Now, here's the thing. Since vita is a positive number, when I add something to it, this becomes larger than vita. And when I have vita and I subtract a little bit from vita, this becomes smaller than vita. Okay, let's write this thing down. So vita plus the square root of vita squared minus omega naught squared will need to be greater than vita, of course, because I'm adding something. And then vita minus the square root of that will need to be less than vita. So this means this exponential is greater. It is more positive than what this is. Now, practically speaking, what this means, since this will always be greater than this, the entire exponential, the entire second term will always be smaller than this. Now I am neglecting C1 and C2. Okay, C1 and C2 control to some extent, yes, the details, but at the end of the day, if I neglect the influence of C1 and C2, then really what I need to think about is what the exponent of these two terms look like. So this is what I'm talking about. I'm focusing on this without the influence of C1 and C2, because that one is not that critical. I want to get insight about the solution, and to get the insight, I don't have to consider C1 and C2. All right. So as I said, this will be greater than that, which means the whole thing, the second term, will be smaller than the first term. This means as time increases, as time goes by, the second term will become smaller and smaller compared to that, which means this will die out first. And this will be greater than the term that will eventually become very small. So really, since I'm adding the two terms, really as time becomes larger and larger, The only term that I need to consider is the first one, because that will be the greatest of the two. And this is the reason why we call vita minus the square root of vita squared minus omega squared. That's why we call this the decay parameter, because this parameter controls how fast the oscillation, how fast the motion goes to zero. Now, qualitatively, what the motion will look like in the case of overdamping, since we do have a strong resistive force added to the motion, there will not be the chance for the system to complete one oscillation that it did with the case where we had underdamping. So this is x and this is time, the time axis. The system will reach a maximum, and then eventually, as time goes to infinity, it will reach a position of zero. It will take some time, of course, to become very small, but it will not have the chance to go up and down as it did where we had underdamping.